So here we have a diagram of a spanner moving a bolt. You can imagine yourself grabbing onto this spanner and pushing around to twist that bolt, and if you're turning it in that direction, you'll be to undo the bolt, you'll be applying a moment. The moment has a twisting action. And how do we work out the value of a moment? The moment is the force that you apply times the perpendicular distance. If you grab this spanner and press straight down like this, press down there, and we have a distance d, the length of the spanner, then we know that the moment that we're creating is that force times its perpendicular distance back to the point P that we're working out the moment around. Okay, so in that case, the moment would be force times distance. Now, we'll just call that force 1 because we're going to talk about a different force now. But we don't always have a perpendicular a perpendicular force times a moment arm to work out a moment. For some reason, sometimes when you're pushing on a spanner, you can't actually press straight down, perhaps because you can't get your arm in that position, and so you actually have to press this way. And if that was the case, if that's your force here, there's your force, how do you actually work out the force times the perpendicular distance? Okay, because this distance is no longer perpendicular to the force. Okay, but what we can do is imagine that when you're pressing down on something, that there's a line of force, there's a line of action going through the object that you're pressing down on, all the way through here. And that line of action always has horizontal and vertical components all the way along it. And we can work out from this point here the horizontal and the vertical components. And the way to get those horizontal and vertical components is to use this line of action of the force as the diagonal of a parallelogram that goes back to the place where you're calculating the moments. Okay, so we want to calculate the moment at there around point P. So we have now this perpendicular distance, this perpendicular component of the force times its distance will be what we use to calculate the moment. Now we know that if you're pressing this way along the oblique, that the vertical and the horizontal components, of course, are going to be smaller than the original force because they're just its components. So how do we work out this vertical component? Well, if we know this angle here, theta, and we know this angle here is theta, this angle here is theta by trigonometry, then we know that this vertical component here is going to be f sine theta. Okay, so we can see that the vertical component is actually smaller than the original force, and the moment is f sine theta, the vertical component, times its perpendicular distance, which is d. So we can see here that when we compare pushing that way in an oblique direction with pushing downwards, that you're actually going to get a smaller moment, so it's less efficient to push this way. When you push straight down on the spanner, your moment is F times D. But when you press obliquely on the spanner, your moment is only F sine theta times D. And because we know that sine theta goes from 0 to 1, F sine theta is always going to be smaller than F. So we know that F sine theta times D, that moment there, is actually going to be smaller than that moment there. So that's to show you that pressing obliquely is actually not as efficient as pressing straight down at a perpendicular angle to the moment arm. Now, this force here also has a horizontal component, but that horizontal component doesn't count. Why? Because it's along the length of the moment arm. And as you can see, if you're pressing that way on the spanner, there's no twisting around the bolt. So there's no twisting this way or this way. So there's no moment due to the horizontal component. So the moment is only due to the vertical component. And we have to work out the sign of that moment. So because we're pressing that way, the vertical component's in that direction, the spanner's going to be down, which is counterclockwise, or tightening, sorry, or loosening something. When you're loosening something, that's a positive moment. So it's a positive sign. Now, sometimes you actually want to work out the moment in a different way. Instead of, you've got your force and you're pressing down through here along your line of action, but for some reason you actually can't work out this, you can't work out the components. So how else can we do it? We know that a moment is a force times the perpendicular distance. Well, what we can do is now take this line of action through here until we come to a point where we can work out the perpendicular distance back to the point P. Now here the force, this is force F here, and the moment is the force times its perpendicular distance. And we know from trigonometry, if that's theta there, that this is d sine theta. So once again, the moment using this method is still, it's F times d sine theta, which is F sine theta times d, just rearrange things, which is the same as it was over here. Because it's going along that way, the bolt's loosening, it's counterclockwise, that's positive. But you can see that you can work out the moment in two different ways depending on the circumstances of your problem. You can either, with an oblique force along a moment arm, you can either work out its components, take the vertical component times the moment arm as the moment, or you can use the force itself and then work out the perpendicular distance back to the point. So you take the force and then you take the moment arm as being d sine theta.